Okay, welcome back to part 2, where we talk more about acids and bases, and we just generally have a good time. I hope you guys had a nice little break. Hope you have some snacks. Let's get started. The second definition of acids and bases is known as the Bronsted-Lowry definition. Bronsted-Lowry definition. And the Bronsted-Lowry definition, it defines an acid as a proton, i.e. H plus ion donor. Okay, so it donates a proton, and a base is defined as a proton H plus ion acceptor. Okay, and both of these are within a chemical reaction. For example, if we have a reaction between HCl in aqueous suspension plus H2O liquid to form H3O plus in aqueous suspension and Cl minus, okay, so right here we have the thing that donates the proton. Okay, that means that it is a Bronsted-Lowry acid. Now, if you look to the other side of the reaction, there is also a species on this side of the equation that can also donate a proton if you go in the backwards reaction direction. Okay? This is also a Bronsted-Lowry acid. For another example, let's look at something that's a base. For example, ammonia, NH3, when it's dissolved in water, can react with water to form, actually let's go ahead and make this a double way arrow because this is an equilibrium reaction, to form ammonia, NH4 plus aqueous, and OH minus aqueous. Okay, now this is the thing that accepts the proton, donates the proton. Okay, so it is a Bronsted-Lowry base. If you look to the other side of the equation, so if we're going back towards the left rather than towards the right, we find that ammonium is also a Bronsted-Lowry base, because if you go back this direction, it's also the one that's donating the proton. Okay, so you have Bronsted-Lowry acid-base pairs. We'll get back to that in a little bit. According to the Bronsted-Lowry definition, acids and bases always occur together. Okay, this makes sense, right? If you have one species that's donating a proton, you have to have another species that's accepting the proton. And vice versa is also true. If you have a species that's accepting a proton, you have to have something else giving you the proton in the first place. Now, let's take a closer look at this reaction we have above. The reaction between aqueous HCl and H2O forming H3O plus aqueous and Cl minus aqueous. Now, let's figure out and let's look at what is the acid and what is the base. In this case, here is the acid. It's the one that's donating the proton, and water is acting as the base. So the acid is the HCl, the water is the base. Okay. Now let's look at our other reaction between ammonia, aqueous, plus H2O, liquid, goes to NH4, ammonium, aqueous, plus OH minus, aqueous. I guess I can move over like that. Okay, so what's happening here? We have the base, which is the thing that is accepting the proton. But in the case of this reaction, the water is acting as the acid. Okay, so this is kind of weird, right? We have one reaction where water is a base and another reaction where water is an acid. This is a pretty special thing. Not everything has this ability to be both an acid and a base. And when something is able to be both an acid and a base, H2O can be acid or base. And when something can do this, it's called, or it's said to be amphoteric. Okay, it's kind of like the ambidextrous of the chemical world. Okay, if you can be both an acid and a base, you're kind of ambidextrous in a way. So amphoteric is the term that's given these special types of chemicals that can be both an acid and a base. Now, if we look at the reverse reaction of this ammonium reacting with water, if we look at the reverse direction, let's write it this way. So we have ammonium reacting with OH minus to give ammonia plus water. In this case, the ammonium is the acid. It's donating. And the hydroxide is the base. It's accepting. Okay. So NH4 and NH3 are conjugate acid-base pairs, or what's called conjugate acid-base pairs. So we have NH4 plus and NH3, conjugate acid-base pairs. Okay, and you can actually mark this out in any of the reactions. Let's write it out for the ammonia reaction. So we have ammonia aqueous reacting with H2O liquid to produce ammonium and OH minus. Okay, so we have on this side, we have the base, because this is accepting, the base is accepting the proton, and this is the acid, this is the thing that's donating the proton, and on this side we have the thing that's donating the proton would be the acid, and the thing that's accepting the proton would be the base. So we have a conjugate acid-base pair between the ammonia and the ammonium, and we have a conjugate acid-base pair between the H2O and the OH minus. Okay, and you can find this in most any acid-base reaction. Okay, for example, if we were to react H2SO4 with water to form HSO4 minus plus H3O plus. We have on this side the acid, this is what's donating the proton. We have the base, this is what's accepting. On this side we have the base, which would be accepting the proton going back, and we have the acid, which would be donating the proton going back. So we have acid-base pairs, acid-base pairs. These are the conjugate acid-base pairs within this reaction. Okay. Let's take a minute to talk about the strength of an acid. the strength of an acid. How strong is an acid? Or how acidic is an acid? This has to do with the extent, the extent of dissociation. Okay, this has to do with the extent of dissociation. If you have what's called a strong acid, you have complete dissociation. Okay. If you have a weak acid, so termed weak acid, you have incomplete or partial dissociation. Okay. And what do I mean by dissociation? Well, I mean literally breaking apart of the molecule that forms up the acid. For example, HCl. The complete dissociation of HCl would be the H plus completely separating from all of the Cl minus that's present in the system. Okay, so we have let's represent our generic try that again. Generic acid we're going to represent as HA. Okay, that's our generic acid. If we react HA with some water, to form H3O plus and A minus. Okay, the strength is represented by this type of reaction. Okay, if we have a double arrow here, that means that both the forward and the backward reaction are more or less possible. That means that this is a weak acid. That means that complete dissociation is unlikely. If we have a full arrow pointing towards dissociation, so for example HA plus H2O liquid, there's no equilibrium here, we're noting, and we're saying that this is just going to completely disassociate into H3O plus and A minus aqueous. Of course, you know from our discussion of equilibrium that a complete disassociation is impossible. This is not actually what's happening. Everything is at equilibrium to some extent, but we say that when something is mostly disassociated, meaning that 99.9999999% of the initial molecule has been disassociated, even though there's maybe a few molecules per liter that are still associated, we state that this is a complete disassociation. Okay, so if you and generally it works out because the amount of substance that's left over that's associated is so tiny that it doesn't really affect any type of chemistry that we do. For example, if we look at HCl, HCl is a strong acid. So when it reacts with water, it completely disassociates into H3O plus and Cl minus. Okay, so if you have 1.0 molar HCl in solution, this necessarily means that you have 1.0 molar H3O plus in solution, and you have 1.0 molar Cl minus in solution. The concentration of H3O plus, it turns out, is an important factor in determining the identity or the acidic character of a solution. So we often talk about the concentration of H3O plus, and we'll get back to that in a little bit. Okay, so remember that concentration of H3O plus is important to talking about chemistry, or the chemistry of acids. Some examples of strong acids are HCl, HBr, HI, HNO3, H2SO4, HClO4. Okay, all of these are listed in some table. Yeah. So in the case, I don't know exactly what the table is in the chapter. You're gonna have to look, but the strong acids are listed in some table. Okay, so with the exception of H2SO4, all of these are monoprotic. With H2SO4, only the first hydrogen is strong. Okay, only the first hydrogen is strong. So when you put this into solution, it completely disassociates into H plus and HSO4 minus. Now the HSO4 minus then can lose its proton, but this is a weak disassociation. So not all of the HSO4 minus is going to completely disassociate into H plus and SO4 2 minus. A little bit of HSO4 minus is going to exist in solution, and a little bit of H plus, extra H plus, is going to be added into the solution from that disassociation. HClO4 is perchloric acid. You guys haven't really seen this or messed with it yet. This is called perchloric acid. It's a very strong acid. And of course, you know the others. Okay, so these are examples of strong acids. How about weak acids? What are some examples of weak acids? Weak acid. Actually, an interesting weak acid is hydrofluoric acid. Hydrofluoric acid is a weak acid. When it reacts with water, it does not completely disassociate. There's actually a large, relatively large percentage of HF that stays as its molecular form. So a solution of HF contains a large number of unionized HF molecules. So these are molecules that are floating around exactly as bonded hydrogen to fluorine in solution. So if you have a 1.0 molar HF solution, you will not have, this does not mean you will have a H3O plus concentration equal to 1.0 molar. Okay, so the H3O plus concentration will be less than 1 molar because some of the hydrogen is still stuck to the fluorine and forming that HF compound. Some examples, other examples of HF, of course, we have hydrofluoric acid, we have acetic acid. Acetic acid is a weak acid, CH3COOH. Carbonic acid is a weak acid. Phosphoric acid. Oops. So carbonic acid is an interesting acid. It's actually, it forms a system of, well, I guess we'll learn about it later in the chapter, but essentially, carbonic acid is very important to our body's ability, or mammalian, or actually it might be animal, not just mammalian, but animal's ability to regulate the pH within the body. Okay, so there's a system of acid and base. If you have the H2CO3, it's acidic. If you have the HCO3 minus, it's basic. And so there's a competition between these two within your body, and it allows your body to regulate or to self-regulate the acidity or the what's called the pH environment of your body, or how acidic your body is. And this is extremely important to different types of chemistries, enzyme chemistry, protein chemistry, DNA chemistry that are all happening inside of you. So if your pH range wanders off and becomes something that it's not supposed to be, this is extremely deadly. And actually, this is called acidosis. When your body starts to get too acidic, it's called acidosis, and it can be quite dangerous. And the reason that this doesn't happen all the time is because we have this system between carbonic acid and bicarbonate in our body that's kind of fluctuating with time and keeping our pH constant, or keeping the acid content constant within our body. Okay, and an interesting thing about phosphoric acid tastes like Coca-Cola. Don't ask me how I know this. I've never tasted phosphoric acid. Actually, I have, because that's what they use in Coca-Cola to give it its classic Coca-Cola flavoring. Check the label of any Coke and you'll see that it has phosphoric acid in it. Yeah, and in this case, I think that it's actually used as a flavoring at this point. Anyway, you can buy phosphoric acid, dilute phosphoric acid, that's used as a sanitation or a sanitizing liquid. If you do certain types of home fermentation processes, which I do. I like to ferment things. And oftentimes you have to sanitize the equipment beforehand so that you don't have any different types of infections that are happening within your fermentation other than the actual infection or fermentation that you want to occur. And so you have to kill off everything beforehand. And a food-safe acid to use for this is phosphoric acid. And this is why I know it tastes like Coke, is because, confession time, I have in fact tasted phosphoric acid. But also you have too, if you've ever had a Coke. Okay, let's end it there. My first part went a little long, so I want to keep this one maybe a little bit shorter. And we will pick up next time on exactly how to quantify the acidity or basicity of a solution. So I'll see you then. I hope you guys have an excellent day. Yeah, stay classy.